Hey math people. So I just gave my identities test to my trig students and it went So I figured I'd make a video of the review trig verification problems to supplement my key that was already online, but hey, that's okay. As one of my students put it best, with some of these trig proofs for verifications, he said that it feels like sometimes you just throw math in there that comes from thin air. Or he said some variation of that, right? Like some of these tricks that we might do in a trig proof or identity verification, it does seem kind of wonky. It seems like, what the heck, how did they create that and why, really? Truly, why is the hard part. So let's do a few identities. I found the 6 from my review guide, so let's do those 6. I'll post these problems too as a worksheet and just check the description for them. Before we get to it, these are the identities that you need to know to do these 6 verifications. Okay, let's assume that my post-editing skills are worthy there. So let's check out the very first one. So as per the usual with trig verifications, we want to work with left and we want to get to the right. So let's play around with this expression right here. So instinctively, it's very tempting to cross these tangent square x's out. No, don't. You end up getting like 0 over 1 or 1 over 1, depending on what your faulty interpretation of it is. So that is not a thing we can do. Obviously, this is what we want to get to. I noticed down in the denominator, we do have an opportunity to employ a Pythag identity. I know that tangent square x plus 1 is equal to secant square x. So with that said, I can actually firstly replace that. So I guess my first step in the process, maybe I'll number them, will be to replace the denominator with a good old secant square x. And it's good practice to write an equality chain here. So like this is equal to this, so on and so forth. So next step, so I'll say the second step, I see that secant square is down in the denominator. I can use a reciprocal identity with secant and rewrite this as tangent square x. Didn't touch the numerator at all. And I can use reciprocal. The reciprocal of secant is cosine. So I can write this as multiply by cosine square x. I guess an optional like step 1.5 would be to rewrite it as tangent square x times 1 over secant square x. That might help some people see what I see. So I'm almost there. I can rewrite tangent using the quotient identity now. So I guess my third step would be to rewrite this as sine square x over cosine square x. That is the quotient identity, which allows me to easily see a potential cancel. Something that a lot of my students like to do is they like to rewrite every trig expression that's just chilling by itself as over 1, and that helps them see opportunities for cancellation. So I'm going to do that just to kind of overemphasize that idea. And now with our final step, I see this move right here. I'm going to say the last piece of the puzzle, you end up just arriving at your answer of sine square x. Next one on our list, we just want to go from this smaller expression, tangent square theta, and we want to get to this larger one. It's got a cosecant and tangent in there. I did write it down correctly. So let's play around with this. I notice a -1. Earlier we used this guy. We used the fact that secant square theta was equal to 1 plus tangent square theta. This is just a Pythag identity. We used this in the last problem. We can use an alternative version here. If I were to try to isolate tangent square theta here, I know that tangent square theta is secant square theta -1. The reason why I'm swayed in that direction is because I see this -1 here. And, well, if I use this identity, that's what I get. One of the hardest, trickiest parts of trig is you can easily go down the wrong path, at least with a verification of identities. If you try to use, let's say, quotient identity there, it's not going to help you out too much in regards to this -1. That's what I see. I'm keeping my objective in mind, right? I know that if I'm driving somewhere, I'm going on vacation somewhere, I'm going to California, I know my destination. I'm not just blindly driving. I have an idea of where I'm going. So that's kind of the logic I employ when using these trig identities here. So I'm going to say the first step, I'm going to equal this to secant square theta minus 1. Okay, I know that cosecant is 1 over sine, and I know that tangent is sine over cosine, and tangent is over cosine. This is an over cosine. The reciprocal of secant is cosine. So how about a good second step is to write this as 1 over cosine squared theta minus 1. Now, this kind of is the step that's hardest to see, and it really is in the same spirit of what my student said, that really, where are some of these expressions coming from? It seems like you're pulling them from thin air. Yeah, is really the answer to that. Yep. So, yes and no, really, because I know that cosecant is 1 over sine squared theta, and I know that tangent is sine squared theta over cosine squared theta. You're multiplying those two. If you notice my expression here, I have the cosine squared theta. I'm going to put a little check there, but I'm missing a sine squared theta over sine squared theta. What do I know about anything over itself that isn't 0? Sine squared theta over sine squared theta, that's just 1. I can multiply this by 1. So I'm actually going to multiply this by, I'll do it in red, I'm actually going to multiply this by sine squared theta over sine squared theta. So check this out. I'm going to say my third step, put the equal. It's going to be 1 minus cosine squared theta, and I'm now multiplying this by sine squared theta over sine squared theta. This is all then minus 1. This is secretly 1, so I'm not changing my expression. Now in this opportunity, I see, really this is just one large fraction. I'm multiplying the top and I'm multiplying the bottom. I can sort of attach this sign with the cosine. It's really not a step. I guess it's like a step 3.5 really. So I'm going to erase this. We're kind of done with this logic here. I'm just going to flip the orientation of this just to help you see what I'm going to do. Actually, I notice that cosecant is here and tangent's here. I'm going to flip the orientation of bottom. You can do this. Let's just say the bottom is like, they're numbers. This is 3 and this is 5, right? 3 times 5 is 15. 5 times 3 is also 15. I can flip the way I write it. So I'm going to write this as 1 times sine squared theta, keeping the numerator completely the same. The bottom, I'm just flipping the orientation of them. So it's going to be sine squared theta times cosine squared theta, all minus 1. And that's kind of like a step 3.5. I didn't really do anything. I just kind of flipped the orientation a bit. So what am I looking at here? I'm looking at like 2 final steps. So I'm going to say step 4. I think I can squeeze everything in here. What do I notice about, I guess I can split it. It's almost like another step 3.7. There's really no need to split it. So what I'll do is just this. I'll just address this. What do I notice about these 2 expressions now that I've kind of reorientated the way that they're written? I know something about 1 over sine. That's cosecant. That's what I was trying to get all along. So I'm actually going to just rewrite this immediately as cosecant squared theta. I'm running out of writing here. I don't really want to write another step. I know that sine over cosine is tangent. Perfectly written out for me right here. And that's exactly what I needed. That minus 1 is just chilling off to the side, and that's the entire proof. So the hardest part here was really just understanding that I can multiply this term by sine squared over sine squared, and that really is a nice little trick from thin air that allows me to rewrite this as the 2 requested trig expressions. Next on the agenda, obviously we have to throw a fraction one in there. I have the difference of 2 gross fractions. We can do this together. We just need common denominators, and a lot of people don't like that. Here's one of the many reasons why. I'd like for you to view both of these as factors, right? And with these factors, you have to treat them differently. You can't just say, oh, this one has a negative sign, so this one needs a negative sign, and this one has a positive sign, so that one needs a positive sign. You can't do that. These are separate, different total factors packaged together. So with that said, this side is lacking this whole 1 minus sine x, whereas this side is lacking this whole 1 minus sine x. So we have to multiply it by exactly that over itself, because that's secretly 1. Let's do that. We got 1 minus sine x over, so I'm multiplying this side by 1 minus sine x over 1 minus sine x. Because that's what the other side has, right? And same story over here, we have 1 plus sine x over 1 plus sine x. And I understand it's pretty small, my writing, but I'm just visually showing you that's what I'm about to do for my first step. So what is that going to look like? Up top, I'm going to have cosine x, and that's being multiplied by 1 plus sine x. This is all over 1 plus sine x times 1 minus sine x. Always close your parentheses. We're subtracting off pretty much the same thing on the other side here. So we have cosine x times 1 minus sine x. This is all over, well, the same denominator, right? That was the whole point. So we have 1 plus sine x times 1 minus sine x. And what a lot of students like to do here is they like to go, hey, I see, I can cancel these 1 plus sine x's, and I can cancel these 1 minus sine x's, and you're back to where you started. So it's tempting to do that, and it's mathematically correct to do that, but why would you do that, right? We're trying to get to here, we're not trying to go back to where we started. So with that said, don't do that. Actually distribute out the top for both cases, and actually, since we have the same denominators now, we can make it one large fraction. So let's do that. So for my second step, I'm going to do a 2-for-1 kind of deal in my simplification here, which in my class it's totally legal to do it this way. Can't speak for everyone, some teachers might be pickier. But I'm going to distribute out the top while I merge it to one fraction. So this is going to be all over. Gotta work on that. Straight lines are difficult for me. All over, they have the same denominator, so it's just over that denominator now. 1 plus sine x times 1 minus sine x. Okay, and the top, this is going to be cosine x, this is going to be cosine sine x when you distribute. And likewise, you have to be careful of this tricky negative here. This is going to be negative cosine x, and this will be a negative times a negative, so it'd be positive cosine x sine x. Yeah, so let's do that. Should be 4 terms. I'm going to get cosine x plus cosine x sine x minus cosine x, hey, look at that cancellation, plus cosine x sine x. Okay, cool. I notice a cancellation, boom, boom. How many cosine x sine x's do I have up top? I have 2 of them, so I stick a 2 in front. So for my third step, maybe I can do another 2-for-1 with the simplifications, which again in my class would be okay. And also I'm running out of board space, so just be wary of that as well. I have 2 of these, so I'm going to say 2 cosine x sine x. What a lot of students like to do is they like to, maybe they write cosine square x, sine square x, that's a common mistake, but you're adding, not multiplying. And another thing students do is they'd say, oh, 2 cosines, so 2 cosine. Oh, 2 sines, so 2 sine. But 2 times 2 is 4, and you don't have 4, you have just 2. So you just stick a 2 in front when you're adding. Alright, so this denominator, I'm going to FOIL this out, distribute the bottom out, binomial times a binomial, so I guess I'll do the math on this kind of off to the side here. So 1 times 1 is a number, that's going to be 1. 1 times negative sine x is negative sine x. Sine x times 1 is plus sine x. That's a nice cancellation already. And lastly, sine x times negative sine x will be negative sine square x, and we like this expression. We like 1 minus sine square x a lot, so that's what I'm going to put here. Firstly, why do I like that thing? Why do I like 1 minus sine square x? It's a pi tag identity, and it's one we used in the very first problem. Really quick, I guess I can prove why we like that. Sine square x plus cosine square x, that's equal to 1. That's your classic pi tag. What I can do is I can subtract good old cosine, well, scratch that. We want to solve for cosine square x. I can subtract sine square x from both sides. I get cosine square x is equal to 1 minus sine square x. That's what I have, right? So I can replace my 1 minus sine square x there with cosine square x. And I'm going to do that for my fourth step. Step 4. I'm going to say this is equal to, same numerator, nothing's going to change there, all over cosine square x. Hey, I'm almost done. Might be a little hard to see, so I might rewrite this to make it easier to see, but if I'm thinking here, how many cosines do I have down below in terms of a product? I have 2 of them. So just for the sake of clarity, so I wouldn't do this if you're on a test, kind of trying to write a compelling argument to someone. I'm just going to rewrite this though as cosine x, to allow you to easily see I have a nice cancellation here. Cosines cancel. I'm left with, for my 5th step, 2 times sine x over cosine x. And I intentionally put this 2 kind of lurking off to the side because I know it's that 2 in my final kind of product there. What is sine x over cosine x using quotient identity for our 6th step? Hey, I'm done. It's 2 tangent x. Alright, so this next one is fun looking, at least, right? I didn't know this before kind of walking into this class this year, that if you have tangent square x minus sine square x, that's actually the same thing as tangent square x times sine square x. Okay, cool. A little bit of work though, unfortunately, at least the way I did it. Maybe there's a faster way. And with a lot of these proofs, keep in mind there might be faster ways. This is just like what I saw. You know, keep that in mind. These are my first instincts. There are other paths, right? There are other ways to get to California, is kind of what I say. So if we're, you're where you're at right now, you're driving to California, there are multiple routes you can take. But anyway, for this one, I see that this is the product here, so it's kind of like one total term. Whereas here I have the difference between these two. I have 2 terms. I want to somehow merge them together, so I got to make them fraction-like in order to do this. I'm going to rewrite tangent square x as a quotient identity. In situations where you just don't know where to start, you got to try, right? You miss 100% of the shots you don't take. I think Michael Scott might have said that at some point, right? So with that said, what I want to do is rewrite tangent square x using quotient identity. Let's just see where that takes me, right? If we have no idea, at least attempt something. But on that same note of similar denominators, I may as well try to get tangent square x with the same exact denominator. As of right now, its denominator is just 1. So what is it missing? It's missing a cosine square x. With that said, let's just multiply this by cosine square x over cosine square x, get those same denominators. Maybe it might result in something, who knows? So I'm going to say this is minus sine square x. So again, I'm multiplying this by cosine square x over cosine square x. Hopefully it takes me somewhere. I'm left with cosine square x over cosine square x. And it doesn't really seem to help so far. It makes it look a lot messier, but let's see what happens. I have the same denominators. At least I can merge these to one fraction now, so that'll be my 2nd step. Let's just make one fraction here. We're going to say sine square x minus sine square x cosine square x is all over cosine square x. Maybe this might help. I notice I now still have those 2 terms in the numerator, but now they have something in common. Now they both have a sine square x in common. I can actually factor that out, so at least it kind of looks like we're heading somewhere with this. Since both of these terms, so I have, this one's just sine square x, this one is sine square x times cosine square x, they both have a sine square x. I can factor it out, and maybe that might lead me somewhere. So my 3rd step is to factor out sine square x, leaving the inside as, well, if you divide sine square x by sine square x, it's the same thing over itself. That's just 1. So if you need the work to see that, sine square x over sine square x, cancel, you get 1. And I guess I'll show the math for this too. So this is a dot, not a square. Sine square x, cosine square x is all over now sine square x. That's what I'm plucking out. I'm dividing both terms by. So cancel, cancel. I'm left with just cosine square x after I pluck out this sine square x. So it's going to be minus cosine square x. I just factored. So maybe I'm going somewhere with this. Who knows? This is all going to be over cosine square x. That was the hard step. Really, when I gave this to some students, it was really, once I got to this point, a lot of people were able to take it home because I know what 1 minus cosine square x is based on what I just talked about in the last problem. This is a Pythag identity opportunity. This is sine square x. So I'm going to rewrite the rest of this. Sine square x times sine square x. It's going to be all over cosine square x. Okay, at this point in the game, some of my students, they multiplied sine square x by sine square x, and they got sine to the 4th x, so that's mathematically true. You can do that, but I don't see how that helps you, right? I know that I want to get sine square x. I don't see a reason to raise that to the 4th power. But what I do know is that I have two expressions now. One of them, sine square x, I'm already halfway there. The other one's quotient identity opportunity here. So for my 5th step, sine square x over cosine square x, that is tangent square x. And actually, I'm done. If you don't know where to go, try something, right? And maybe you get partial credit, who knows, as long as it's right. In this case, I didn't see an opportunity to use a Pythag identity, at least it didn't seem too immediate to me. I knew that I wanted to kind of merge them together somehow. I did that by getting common denominators and using quotient identity in that process with tangent square x. So the next two aren't too crazy. I think the last one was actually the craziest one we did. This one just requires one of those identities that we don't really use all too often. It's sum and difference for sine. I notice I have the sum inside of a sine expression. I can rewrite this as, so first step, and this is just the definition. So anytime you see some sort of addition or subtraction inside of your trig function, you should look to see if that's a sum difference formula. So I see it's a sum. I can rewrite this by that formula, which I'll just flash right now. Yeah, by this guy. I can rewrite this as sine 270 cosine x plus cosine 270 sine x. Kind of went through that a little slowly there, step by step. This is your first value, this is your second. It's plug and chug. We like this actually. This looks pretty good to me. I know the cosine of 270. I know the sine of 270. So for a reasonable second step, I'm merely evaluating what those are. So sine of 270, think about your unit circle, you're all the way at that lowest value. Sine is the y component, so that's a -1. I can just plug that right on in. So that's -1 times cosine x, and this is going to be plus. Well, at that point, and I can draw it, I don't know why I'm visualizing in my head without drawing it, all the way down here, so this is 0, -1. The -1 is the y value, the 0 is the x, so this is actually just good old 0. And what do I know about 0 times any expression? Gone. Anyway, I'm already done, right? I can actually just say third step and rewrite my final answer here. It's negative cosine x. So what is the hard part of this problem? It's using this formula that almost no one ever uses. I don't use it all too often, at least. Maybe that's a mathematical sin on my end, mathematical sign on my end. But really, I don't know, just knowing that formula in itself is sometimes hard enough. Last one here is the same spirit, except now we have two of them we have to play around with. So maybe I will color code them. So I will do black for the first term, red for the second. So for my first step, just using the definition here, I'm going to have sine x cosine y plus cosine x sine y. Okay, cool. And I'm going to add, that's what we have here. I said I would write this one in red, so I will. Sine x cosine y. It's going to be now minus cosine x sine y. So I'm just using the definition in both cases. So I see a cancellation. I have cosine x sine y, except this one's negative. This cancels. Don't want to merge the colors there too much, it messes up the markers. So what am I left with? So step 2, I'm left with sine x cosine y, and this is then plus sine x cosine y. Hey, look at that, two of the same things. I'm pretty much done here. My last step, step 3, just merge them together. 1 plus 1 is 2. I have 2 sine x cosine y's. So just know 1 plus 1 is 2 and you got this. I know this stuff isn't easy. You gotta play around with it. That's the best way to learn. It's just to go at it over and over and over again. And sometimes it's a little rewarding when you look and stare at it enough times or go through enough failed attempts. It's a little rewarding the moment you finally see the solution, because then you can just run away with it. And that's one of the best feelings in my opinion, is when you know the solution to a proof, you just see the end in sight and you're kind of like far away from it, but you see it and you just run with it and you just keep going and going and going until you're there, and you feel like a genius at that point, you know, because you were sitting and staring at it for so long and it's finally in your head and you're like, bam, I'm a mathematician. And you are. So even if you are having a hard time with this, you are a mathematician. You made it this far. So I'm going to continue to math on. I hope you do the same. Good luck on your trig test, or at least continuing your trig test on Monday if you're my students. Okay, bye. Math on, yeah.